Hi everybody, this is part 2 of the lecture to accompany chapter 3 in your textbook. Please carefully read chapter 3 as there are a lot of great examples and illustrations that will help you understand the material, and I simply don't have time to address them in this lecture. Okay, let's move on to look at common patterns of deductive and inductive reasoning. We're first going to look at the common patterns associated with deductive reasoning, and they are hypothetical syllogisms, which use the conditional statements that we learned about in chapter 2. Categorical syllogisms, which use words like all, some, or none. Arguments by elimination, in which possibilities are eliminated one by one until only one conclusion exists. Arguments based on mathematics, which is just like it sounds, you use math to get to the conclusion. And arguments from definition, where the conclusion is based on the definition either inherent or understood in the premises. So let's look at each of these in turn. Hypothetical syllogisms are arguments that contain two premises and a conclusion. At least one of the premises is a conditional if-then statement. There are three kinds of hypothetical syllogisms: modus ponens, chain arguments, and modus tollens. Let's look at each of them. First, modus ponens. It has the structure, if A, then B. A, therefore B. So here's the example. If it rains, which is A, then I will get wet, which is B. It's going to rain, A, therefore I will get wet, B. Pretty straightforward. The next kind, chain arguments, link two conditional statements together to come to the conclusion. The structure is, if P, then Q. If Q, then R. Therefore, if P, then R. This example, if we don't stop for gas soon, which is P, we will run out of gas, which is Q. If we run out of gas, Q, we will miss the party, R. Therefore, if we don't stop for gas soon, P, we will miss the party, R. You can see by this example that it works logically. And finally, we have modus tollens. If A, then B, not B, therefore not A. And the example, if we are in Reno, which is A, then we are in Nevada, which is B. We are not in Nevada, which is not B, therefore we are not in Reno, which is not A. In all of these structures, you can see that the conclusion logically follows from the premises. They are what's called logically reliable. In other words, as long as all the premises are true, the conclusion is guaranteed to be true. There are, however, some incorrect or invalid forms of hypothetical syllogisms out there, but people often use them when they're arguing. They think they are valid, but they are not valid. And if you can learn to spot them in an argument, good for you. There are two types: denying the antecedent and affirming the consequent. Basically, they're just getting the argument backwards. The first one, denying the antecedent, is the backwards version of modus tollens. Modus tollens is if A then B, not B, therefore not A. It makes sense that way. But denying the antecedent says if A then B, not A, therefore not B. Here's the example. If we're in Houston, then we are in the United States. We are not in Houston, therefore we're not in the United States. You can see that even though it's possible that both the premises are correct, but the conclusion is false. And that can't be if it's a valid hypothetical syllogism. The second one, affirming the consequent, is the backwards version of modus ponens. Modus ponens is if A then B, A therefore B. But in affirming the consequence, the pattern is changed to if A then B, B therefore A. So here's the example. If we're on Neptune, then we are in the solar system. Well, that's true. We are in the solar system, which is also true. Therefore, we're on Neptune. Obviously, that's false. These are still considered deductive, even though they're invalid, because people tend to think that they're valid when they use them. They should be considered deductive because they're meant to be deductive, even though their structure is incorrect. The second pattern of deductive reasoning is the categorical syllogism. These also consist of two premises and a conclusion. In this case, however, they begin with the words all, some, or no. Basically, the argument has to do with putting things into categories. Here are some examples. All A's are B's, all B's are C's, therefore all A's are also C's. And the example is all oaks are trees, all trees are plants, therefore all oaks are plants. Makes logical sense. Some A's are B's, all B's are C's, therefore some A's are C's. And here's the example. Some frogs are cats, all cats are dogs, therefore some frogs are dogs. Now, remember, we're looking at structure, not the truth of the premises at this point. Structurally, this is correct. Finally, no A's are B's, all B's are C's, therefore no A's are C's. No cats are dogs, all dogs are canines, therefore no cats are canines. Again, the conclusion logically follows from the premises. Arguments by elimination seek to logically rule out various possibilities until only one single possibility remains. I'm a big puzzle fan, and one of the types of puzzles I like are these kinds of word problems. They can get very complicated, but let's look at some fairly simple ones. The first one, A or B, not B, therefore A. In the example, either Joe walked to the library or he drove. Joe didn't walk to the library, therefore, Joe drove to the library. If it's either or, and one is not the case, then the other one, by elimination, must be the case. P or Q. If A, then not P. A, therefore Q. And that's a little bit more complicated, but it makes sense when you put it a word problem. Either Sam committed the robbery or Ethan did. That's either P or Q. If the robber had a gun, which is A, then Sam didn't do it, which is not P. The robber had a gun, which is A. Therefore, Ethan committed the robbery, which is Q. So you can see it fits logically into that pattern. Now, we may do some more complicated ones of these in class. Mathematics is deductive by nature. Math seeks to find a single answer to a problem. It's a model of logical step-by-step reasoning. So generally speaking, if there's an argument in which math or some mathematical calculation or measurement is involved, you can assume that it's a deductive argument. As you can see in these examples, the conclusion follows necessarily from the premises. There are 4 A's and 2 B's, therefore there are 6 things altogether. 8 is greater than 4, 4 is greater than 2, therefore 8 is greater than 2. These are deductive. The final type of deductive argument is argument from definition. In this type of deductive argument, the conclusion is presented as being true by definition of some key word or phrase, either the dictionary definition or the commonly accepted definition of the word or the phrase. Here are some examples. Bob is a bachelor, therefore Bob is unmarried. The definition of bachelor is commonly accepted to be that of an unmarried man, so the conclusion logically follows. Janelle is a cardiologist, therefore Janelle is a doctor. A cardiologist is a kind of doctor, so the conclusion that Janelle is a doctor logically follows from that. Okay, let's move on to typical inductive reasoning patterns. Remember, in inductive reasoning, you're not coming to a precise conclusion. You're looking for things that are probably or likely to be the case. Here are some typical inductive patterns. Inductive generalization is where you come to a general conclusion based on specific instances or examples of what you're talking about. Predictive argument is where you make a prediction about what will happen in the future based on what happened in the past. An argument from authority is the kind where you use some kind of presumed authority, like an expert or some kind of witness, as evidence to support your conclusion. In a causal argument, you're linking something that occurred to an earlier occurrence and saying that one thing caused another to happen. A statistical argument is obviously based on using statistics as evidence to support a conclusion. And an argument from analogy is where you compare 2 or more things and say that they're alike enough in some way that what's true for one thing is also true for the other thing. So now let's look at each of these kinds of inductive arguments individually. When we generalize, we come to a conclusion based on our observations about particular things. If we see the same thing happen often enough in a particular situation, it's natural for us to come to the conclusion that that's the thing that generally happens in that situation. Do we know that's exactly what happens every time in that situation? Not necessarily, but that's what inductive reasoning is all about. The common form is this. So far, the bees I have observed have had the property P. Therefore, all bees probably have the property P. I put the word probably in there just to let you know that it isn't 100% certain based on the evidence that all bees actually do have the property P, just the ones I have observed, so that makes it inductive. In this example, I come to the conclusion that people from Iowa are friendly based on observations. There's 3 observations. I met a farmer from Iowa and he was friendly. I met a dentist from Iowa and she was friendly. I met an insurance salesman from Iowa and he was friendly. So I guess most people from Iowa are friendly. Is that a certainty? No. It's a probability, so it's inductive. Predictive arguments are kind of the same thing as inductive generalization. But instead of coming to a conclusion about what is the case, you come to a conclusion about what will be the case. In other words, you make a prediction about the future based on your observations. So your conclusion is a prediction about what will happen or what will be true in the future. The common form is, so far all the bees I have seen have had the property P. Therefore, the next bee I see will have the property P. Most U.S. presidents have been tall, therefore the next president will be tall. Now, because nothing in the future can be predicted with absolute certainty, whenever someone argues that something will be the case, it's highly likely that they are arguing inductively. There are examples, however, where predictions are made deductively. Some conditional if-then statements are used as evidence that something will happen, and that makes them deductive, as in this example. If Amy goes, then Ted will go. Amy will go, therefore Ted will go. But generally speaking, unless the argument is structured as modus ponens like this one, predictive arguments are inductive. In an argument from authority, the arguer is using the testimony of someone else as evidence for their conclusion. Usually that someone is a presumed authority on a subject, like an expert or someone with some experience about the topic, or a witness to an event. The common form is, P said that A was true, therefore A is true. So here's the example. The encyclopedia said that bats eat bugs, therefore it is likely that bats eat bugs. In the first example, the authority is the encyclopedia, which we assume to be a reputable authority. Here's the second example. There are bears in these woods. My neighbor Frank saw one last week. The authority in this case is my neighbor Frank, so depending on my knowledge of Frank, I might believe what he says on this topic. The thing about sources of information is that they may or may not be reliable. Because of this, the conclusion you come to based on the evidence is not guaranteed, and so these arguments are inductive by nature. Obviously, good, solid, reliable sources are much more likely to yield good, solid, reliable information. So the better the source, the better the argument. In a causal argument, the arguer is asserting or denying that something is the cause of something else. So X causes Y is the basic form, or as it says here, X is true. The likely cause of X being true is Y being true. Therefore, Y must be true. The example is, I can't log in, the network must be down. Or in longer form, I can't log in. The likely cause of me not being able to log in is that the network is down. Therefore, the network must be down. Now, the entire universe runs on cause and effect, but it's often very difficult to say with 100% accuracy that one thing caused another thing to happen. For instance, in the example, there are several other reasons why a person might not be able to log into a network. Maybe their password has expired, or maybe they didn't pay their Wi-Fi bill. Also, lots of effects have a multitude of causes. You can pick one of the causes out, but that doesn't mean other things didn't play into the thing that's happening. So it makes sense to consider causal arguments for the most part to be inductive. Statistical arguments use statistical evidence to prove a conclusion. In other words, you give evidence that some percentage of a group has some particular property. In a common form, it goes something like, A large percentage of B's have property P. X is a B, so therefore X probably has property P. Here's the example. 83% of Notre Dame students are Catholic. Bob is a Notre Dame student, therefore Bob is probably Catholic. Well, Bob obviously has an 83% chance of being Catholic, but he also has a 17% chance of not being Catholic. So, because stats tend to be generally reflective of the population, but obviously not reflective of 100% of the population, these arguments are usually inductive. However, the final example here is actually a deductive statement. The arguer uses statistics, but they're using it in a conditional if-then format. So because the structure of this argument is deductive, you would consider it a deductive argument. If 65% polled will vote Democratic, then the Democratic nominee will win. 65% polled will vote Democratic, therefore the Democratic nominee will win. But generally, arguments that use statistics as evidence are considered inductive. The last pattern of inductive reasoning we're going to look at is argument from analogy. An analogy is a comparison of two or more things in which the arguer claims that they're alike in some relevant aspect, so they must be alike in other aspects. So here are a couple of examples. Example 1, Hershey Park is a great amusement park and it has a great roller coaster. Dorney Park is also a great amusement park, so Dorney Park probably has a great roller coaster. In the second example, lettuce and spinach are both green vegetables that are considered healthy. I don't like lettuce, therefore I probably won't like spinach either. So in both of these cases, what I'm doing is comparing, well, in the first one I'm comparing two different amusement parks together and saying they are alike enough that what is true about one is probably true about another thing. And in the second example, I'm comparing green vegetables and saying, since I don't like one kind of green vegetable, I probably won't like the other kind either. This part of Chapter 3 was devoted to understanding the different patterns that deductive and inductive arguments take. It's really important to know what kind of argument you're looking at, because in the next part of this lecture, you're going to need that information so you can tell if the argument is well-reasoned or poorly reasoned. This is the end of Part 2. Go ahead and move on to Part 3 of Chapter 3.